This is Lesson 13 in our Calculus 2 series, Partial Fractions. In this lesson, we learn a method for integrating a proper rational function. And when I say a proper rational function, I'm talking about a rational function where the degree of the numerator is less than the degree of the denominator. And the idea of this method of partial fractions comes from making a common denominator to add or subtract fractions. So for example, if we want to add 2 over x plus 2 plus 3 over x minus 1, we know that we need a common denominator. So when we combine these fractions, we get 2 times x minus 1 plus 3 times x plus 2, and we simplify that to 5x plus 4 over x squared plus x minus 2. Now, the idea of partial fractions says if we want to integrate this rational function, we should write it as the sum 2 over x plus 2 plus 3 over x minus 1 because these are easy to integrate. We'll do the first one using a u substitution, but then we'll notice that we typically won't need to do that for these types of problems. If we let u be x plus 2, then du is dx, so this integral can be written as 2 over u du. So integrating gives 2 ln absolute u, or 2 ln absolute x plus 2. Now notice because the coefficient of x here is 1, du is exactly dx. So it's a perfect u substitution. We don't need to adjust by any constant factors. And we have 2 ln absolute x plus u. So here, same thing's going to happen. We don't need to go through all the work of the u substitution. We can just recognize that because u is x plus or minus a constant, it'll make a perfect u substitution, and we'll get 3 ln absolute x minus 1 here. Now, most of the work in using the method of partial fractions is going from the original rational function to its partial fraction decomposition. So how do we get from 5x plus 4 over x squared plus x minus 2 to the sum of 2 over x plus 2 plus 3 over x minus 1? How do we get from here to here? That's most of the work with the method of partial fractions. So these are the steps for the method of partial fractions. The first thing we need to do is factor the denominator completely. Then we're going to set up our partial fractions with the proper numerators, and we'll see that linear factors get constant numerators, quadratic factors get linear numerators, and when we have repeated factors, we want to count up to the multiplicity. And this will all make sense in a couple minutes when we go through the next example. Then we want to find the coefficients, and we're going to have two methods by which you can do that, and then we want to integrate. So taking a look at the same example, starting with 5x plus 4 over x squared plus x minus 2, the first thing we want to do is factor the denominator completely. So from here, we have a denominator of x plus 2 times x minus 1. The next step is to set up the partial fraction decomposition with proper numerators. So each of these factors here are linear. So linear factors get a constant numerator. So we're going to have a over x plus 2 and b over x minus 1. Now from here, we're going to combine our fractions. And so now we have two expressions for the same fraction that have the same denominator. So that means their numerators must be equal. So that says 5x plus 4 must equal a times x minus 1 plus b times x plus 2. And this must be true for all x. So how are we going to find a and b? Well, we have two methods. The first is to multiply out on the right-hand side and collect like terms. So here we have ax minus a plus bx plus 2b. And then let's collect the x terms and collect the constants. So we have a plus b quantity times x, and then we have plus the constant of negative a plus 2b. Now this must equal 5x plus 4 for all x values. That says the coefficient of x here must equal the coefficient of x here. So 5 must equal a plus b. Also, the constant here must equal the constant term here. So 4 must equal negative a plus 2b. Now we have a system of two linear equations in two variables, and we could use either elimination or substitution to solve. Here, it's quite easy to use elimination by just adding the two equations together because the a's will cancel out. And so we get 3b is equal to 9, so b must equal 3. And then plugging into either of these equations, we'll get a is equal to 2. And so now we have the coefficients 2 and 3 that we need for the partial fraction decomposition. And we can go and integrate from there. That's method 1. Method 2 I find to be a little bit easier, so I tend to use method 2. Now we know that 5x plus 4 must equal a times x minus 1 plus b times x plus 2 for all x. Well, if this is true for all x, then how about we choose some convenient x values that will simplify this equation. For example, if we choose x equals 1, this term is going to go to 0, and then we'll be able to solve for b. So letting x equal 1, on the left-hand side we get 5 times 1 plus 4. On the right-hand side we get a times 0 plus b times 3. And so we get 9 is equal to 3b and b is equal to 3. Notice there's another convenient value for x that we can plug in. We can plug in x equals negative 2. That's going to make this term go to 0 and we can solve for a. So 5 times negative 2 plus 4, that's a negative 6, is equal to a times negative 2 minus 1. So a times negative 3. And then a must equal 2. And so again, we have found our partial fraction decomposition and we can integrate from there. Let's take a look at an example where we have a repeated linear factor. Well, first I should say, let's notice that this is not a g prime over g situation. Because remember, if we let u equal x squared minus 6x plus 9, then for du we would need a 2x minus 6. And we don't have a minus 6 up here in the numerator. So we can't do a u substitution of that type here. But we do notice that the denominator is factorable. So let's factor. This is 2x over x minus 3 quantity squared. And notice we have a linear factor, but it's repeated. So when we set up the partial fraction decomposition, we have to count up to the multiplicity. So we need an x minus 3, and the next term we have has denominator x minus 3 quantity squared. We need to count up to the multiplicity. So for example, if it was 2x over x minus 3 to the third, we would have 3 fractions in our decomposition. We'd have denominators x minus 3 squared, and x minus 3 to the third. We have to count up to the multiplicity of the factor. So here it's a repeated linear factor. It has multiplicity 2, so we have x minus 3 to the first and x minus 3 squared as our denominators. And because this is a linear factor we're talking about, they all get constant numerators. Even if we had multiplicity 3, they all get constant numerators. It doesn't count as a quadratic or a third degree denominator. It counts as a linear factor that is repeated. So linear factors get constant numerators. And so we're here. So now let's combine our fractions here. So we need a times x minus 3 plus b in order to combine with that common denominator. And so this says that 2x must equal a times x minus 3 plus b for all x. So again, I'm going to use method 2 and find some convenient values for x. I see x equals 3 would be convenient because it'll make this term go to 0. So letting x equal 3, we have 2 times 3 is equal to a times 0 plus b. So b must equal 6. But now notice there's not any other super convenient value for x. In other words, there's no other value for x that's going to make one of these terms go to 0. So what we want to do in this case is take the b that we just found, b is equal to 6, and plug it back in to the equation. So now we have 2x is equal to a times x minus 3 plus 6 for all x. And we can choose any x value to continue. This is true for all x, so when x is equal to 1, for example, 2 times 1 must equal a times 1 minus 3 plus 6. So we have 2 is equal to negative 2a plus 6. Negative 4 is equal to negative 2a, or a is equal to 2. And you could have used any x value you like other than the x equals 3 that we already used. And you'll get the same answer. So a is equal to 2, b is equal to 6, and we have our partial fraction decomposition here. And so now we're ready to integrate. So our original integral can be broken up into these two integrals now. This first one we know is going to be 2 ln absolute x minus 3. But let's take a look at the second one here. We need a u substitution. U is equal to x minus 3, then du is equal to dx. So this is 6 over u squared, or 6u to the negative 2 du. So integrating, we get 6u to the negative 1 over negative 1. So that's a negative 6 over u, or a negative 6 over x minus 3. And so that completes our integral there. Now I want to point out for this particular problem, it is possible to solve this one using u substitution without partial fraction decomposition. So when we factored here and wrote it as 2x over x minus 3 squared, we could let u equal x minus 3. And then du is equal to dx. And so in the denominator we have u squared. Here we have du. And in our numerator we have 2 times x. If u is equal to x minus 3, then x is equal to u plus 3. And so here we have 2u plus 6 in our numerator, and we can break that into two separate fractions, 2u over u square plus 6 over u square. Simplifying here, we have 2 over u, and this is 6u to the negative 2, and integrating, we get the same answer we had above. Let's take a look at another example. This also has a repeated linear factor. I'd like you to pause the video, please, and work on this one. Here, factoring our denominator, we first factor out an x, and then factor the remaining quadratic to x plus 1 squared. So we have x times x plus 1 squared. So our partial fraction decomposition is going to look like a over x plus b over x plus 1 plus c over x plus 1 quantity squared. So we have the factor of x showing up once, and we have the factor of x plus 1 showing up twice, so we need to count up to the multiplicity. Now we want to combine these three fractions so we can equate our numerators. So we need to multiply a by x plus 1 quantity squared. We need to multiply b by x times x plus 1, and we need to multiply c by just x in order to get this common denominator that we're looking for. So now we could equate our numerators, and we know that this is true for all x. So let's choose some convenient values for x. The first convenient value I notice is x equals negative 1. That's going to make the first two terms go to 0. And we're left with negative c on the right-hand side. And so we have negative 4 is equal to negative c, or c is equal to 4. Now we take this 4 and let's plug it into the original equation. And so now we know that this is true for all x. Now we have our 4 in there. We also notice that there's another convenient value for x we can choose. We can choose x equals 0. That'll have these two terms go to 0, and we'll be able to solve for a. So when x is equal to 0, on the left-hand side we get 3, on the right-hand side we get a. So a is equal to 3. So now let's take that 3 and plug it in for a and rewrite our equation. So now we just need to solve for b. We can take any x value we choose. I like simple ones. I choose x equal 1 here. On the left-hand side we have 16. On the right-hand side we have 3 times 4 plus b times 2 plus 4. So we get 2b is equal to 0, or b is equal to 0. So that tells us that our partial fraction decomposition looks like this. And of course we're not going to include this middle fraction, but I just wanted to show it for completion. And so our original integral can be written as the integral of 3 over x plus integral of 4 over x plus 1 quantity squared. So here we have 3 ln absolute x. Here we have a little u substitution. And so that's minus 4 over x plus 1 plus c. Let's take a look at another. And this problem has a quadratic factor. When we factor our denominator, we see we can factor an x out and we get x squared plus 1. Now this is quadratic and it cannot factor any further. So our original rational function can be written this way. And so our partial fraction decomposition is going to be a over x plus bx plus c over x squared plus 1. We said above that for quadratic factors, we need linear numerators. So here we have a bx plus c as our numerator. And again, the method is the same. We combine our fractions here. So a times x squared plus 1 plus bx plus c times x is our new numerator. And please don't forget to use parentheses here. I can't tell you how many times I see mistakes with that. So we can equate our numerators. And we're here. And this is true for all x. Choosing x equals 0 would make this term go to 0 and let us solve for a. So let's do that. X equaling 0, we get 2 on the left-hand side, and we get a times 1 on the right-hand side. So a is equal to 2. Now, we don't really have any other super convenient values for x, so let's just choose some simple values. I'm choosing here x equals 1. On the left-hand side, I get negative 1. On the right-hand side, I get 4 plus b plus c. And so this is telling me negative 5 is equal to b plus c. But that's all it's telling me. I can't solve for either b or c yet. But that's okay. I'll hang on to this equation, and I'll use it with another one we get when we choose the next x value. So now let's choose another simple x value. I choose x equals 2. And from x equals 2, we get negative 10 is equal to 4b plus 2c. So now I have negative 10 is equal to 4b plus 2c. I already had negative 5 is equal to b plus c. I have two equations in two variables, and now we can solve for b and c. So I'm going to write b is equal to negative c minus 5. And then this b gets replaced by negative c minus 5. I'm using substitution here. And so simplifying, we get c is equal to negative 5. And by plugging that into either of the equations, we get that b must equal 0. So here we had a over x plus bx plus c over x squared plus 1. b is equal to 0. That gives us a negative 5 over x squared plus 1 here. And a is equal to 2, so we have a 2 over x here. So now our original integral can be written as the sum of these two integrals. So we have 2 ln absolute x minus 5 arctan of x plus a constant. Now we've been looking at proper rational functions so far. Those are rational functions where the degree of the numerator is less than the degree of the denominator. Well, what happens if we have improper rational functions? For example, if the degree of the numerator is greater than the degree of the denominator, we need to divide out using long division. So just as a reminder, let's take a look at long division with numbers, and then we'll do it for this rational function. If we were dividing 1702 by 5, we would see how many times does 5 go into 1? It doesn't. So how many times does 5 go into 17? It goes 3 times. So we write 3 times 5 is 15. We write that here, and we subtract, and we're left with 2. Then we bring down the 0. How many times does 5 go into 20? It goes 4 times. 4 times 5 is exactly 20. So we subtract, we get a 0, and we bring down the remaining 2. 5 does not go into 2, so what we have found here is that 1702 divided by 5 is equal to 340 remainder 5, or 340 and 2/5. Now how does it apply for polynomials? Here we have x to the third plus x, and we want to divide it by x squared minus 1. So we have x to the third plus x as our dividend, and we want to hold the places for all the powers of x that aren't showing up here. So this is x to the third plus 0x squared plus 1x, and then plus 0 to hold the place for the constant there. And now how many times does x squared minus 1 go into x to the third plus x? Well, let's look at the highest powers. How many times does x squared go into x to the third? Goes in x times. So we're going to put an x over the x column. Now we multiply through just like we did here. 3 times 5 is 15, and we subtract. Here we multiply through. X times x squared minus 1 is x to the third minus x. And then we subtract. Here we get 0, here we have 0, here we have, now this becomes plus x, so we have a 2x. And we bring down our 0, and we realize that x squared minus 1 does not go into 2x. So x to the third plus x over x squared minus 1 is equal to x plus 2x over x squared minus 1. The same way 1702 over 5 was equal to 340 plus 2 over 5. So now we can replace our original rational function by x plus 2x over x squared minus 1. And now in this case, this integral on the right can be solved by u substitution. So here we have x squared over 2 plus ln of absolute x squared minus 1 plus a constant. And just keep in mind, after you do the long division, you still may need to use partial fractions. It depends on the problem. Now, what if the degree of the numerator is equal to the degree of the denominator? You can use long division, but I prefer the plus and minus trick. Here we have x squared minus 2 over x squared minus 4. And I look at this and think, wow, it would simplify really nicely if this was a minus 4 up here. Right? It would just be 1. So why don't I put in a minus 4 and then add 4 as well? So we have x squared minus 4 plus 4, and then the original minus 2. And now let's write this as two fractions. X squared minus 4 over x squared minus 4 plus, this simplifies to a 2 over x squared minus 4. Now we've got the sum of these two fractions. On the left we just have 1, and that integrates to x. And here we have a partial fractions problem. And so here's our solution, and let's take a look at how we get there. We have 2 over x squared minus 4. So let's factor our denominator, x plus 2 times x minus 2. And these are linear factors, so they get constant numerators. We combine the fractions and then set equal our numerators. We choose two convenient values for x. We choose positive 2 and negative 2. That allows us to find both a and b. And so this is our partial fraction decomposition. And since they're fractions, instead of writing them in the numerator, I just pulled them out of the integral. And so we're here. Now, before we conclude this lesson, let's take a look at the integration tools that we have. We have our basic integration rules. And if our integral is not a basic integral, we know we should be looking out for a composition of functions, or a g prime over g, so that we can use u substitution. If we can't use a u substitution, we look out for trig substitution. But keep in mind that you should always be looking for substitutions before you try integration by parts, because many of the substitution problems look like a product. But in order to get a correct solution, you have to treat them as substitutions. You have to treat them as compositions, rather than starting with integration by parts. I often see students try to use integration by parts for these kind of substitution problems, but then they can't properly compute v from dv. And so I can't give any credit on that kind of solution. And now we also have the method of partial fractions for proper rational functions. And I encourage you to practice integration using all of these tools because it's really the only way to get good at these problems. And with this, we'll conclude our lesson on partial fractions.